Forward to the cloud. Okay, great. Good afternoon. Welcome back from your weekend. Today, the plans are a little bit different, a lot different from what I had originally had planned. There's some issues in connecting a Raspberry Pi to the network for remote access through SSH. So what I'm going to do is pivot a little bit to the survey and the persona to give some time to get the issue resolved with ITS. And so what I'll do today is introduce aspects of the Raspberry Pi, and I'll demonstrate the Unix command line, which the Raspberry Pi uses on Mac OS, but it's the same Unix command line interface, only instead of logging into the Raspberry Pi and showing it to you directly on the Pi, I'll just show you what these commands do on the command line interface for Mac OS. Okay? All right. So I apologize for those technical difficulties. I don't have knowledge of the precise network architecture at the university. So let me make sure I'm still recording. All right, why don't we get started? But before we begin, some administrative bits, and I will answer some questions or open it up the floor for some questions after I give the administrative information. The reading has changed. I think I forgot to update it on the Moodle site. Please read through materials on the Raspberry Pi. There are some there. There are some more that will be popping up fairly soon, right after class. And also, please make sure you are browsing through the Wi-Fi NINA documentation, specifically the APIs that will be relevant for the new upcoming project, which will extend what we have due this evening to device communication. And so instead of implementing a website, you'll just be implementing a server that returns back character information, specifically to report sensor information that'll be displayed on an LCD display. And the LCD display will take the role of a client, which will request from this server with your sensors, request the sensor information. So project number 5 is due this evening. Project number 6 extends that for device-to-device communication, and that will be due a week from today at the usual 1 second before midnight. And so any questions about project number 5? I know there's some questions. I'll open the floor now. Yes. Okay, sure. Mm-hmm. Just TCP is fine. I mean, you could use UDP, but the question was more intended to say if you were just using socket communication for just arbitrary character data and not a well-formatted request and reply for HTTP. And so you can choose to use the secure libraries if you want to. That's not part of the spec. You could choose to use UDP. My expectation was TCP, but I left it open on purpose. But it's more intended for data communication, not HTTP requests and responses. Okay. Any other questions? Questions? Yes. Well, the SSL requires 2 roles on the endpoints because you encrypt with an encrypted connection, you send the session key. And so it's going to require server-side activities, yes. But with that, I'm not requiring you to implement it, just to more discuss how it would change. And that those questions are on purpose because they're preparing you for project number 6. Okay. Does that make sense? Yeah, okay. Any other questions? Yes? Yes, yes. So again, with sending an HTTP GET request on the server side, the assumption is the well-formatted HTTP GET request. So you're going to be doing specific parsing, looking for specific lines, and assuming certain delimiters. But when it's just data, you have to find a way to represent the command to get temperature, get humidity. I'm sorry, get humidity. Brain hiccup. It was humidity and what's the other one? Humidity and temperature. Thank you. We get temperature and humidity, and you're just gonna just invent or brainstorm a way to do that just with character data and not with HTTP GET request. Because if it's an HTTP GET request and it's an arbitrary client, now you have to implement the parsing of the response for that sensor that retrieves the information. But for project 6, which will be for next week, with this device-to-device communication, you wouldn't expect to spend the computation power, as it were, on the Arduino that hosts the LCD display. You wouldn't expect it to spend its computation to parse HTTP responses. You just want to send a request, get back the character data, interpret it as some number, and then use it. Okay? All right, any other questions? No other questions? All right, so why don't we continue on? And again, my plans that I originally had for today were completely dashed, but I can still show you locally on my Mac in a terminal window. I can still show you aspects of the command line interface. Just to kind of get a sense of who we have in the class. Has anyone ever used Linux before or the command line? Oh, everyone has. Okay, a little bit. Feel conversant, or do you use Unix for your everyday work, or mostly Windows and user interfaces? Mm-hmm. Mm-hmm. Okay. Yes. But I see. I see. Because in order to get those applications to run, you need the application frameworks, things like the windowing libraries and other utilities. And that implies that it's going to be ported to that particular flavor of Linux. The kernel is all the same, but the support libraries have to be available and implemented for that particular variation of the kernel. So yeah, it's sort of good news and bad news, right? It's free, but there's still a cost, so to speak. Okay. All right. Why don't we get started? And so where we last left off, to jar your memory, we talked about the schema, as it were, of an HTTP request. And that general schema, when we talked about it, it was purpose with pointing out what the delimiters were, because on the server, when this GET request arrives inbound from the client over the connection socket, you need to chop it up and interpret the fields and the values in the various fields as prescribed by HTTP 1.1. Then we also talked about useful routines to help you in parsing strings, one of which is index of, and we said there were two versions, one that takes the value, which is a character, and the other that takes a value in a starting location. And one of the nuances here is that because we're talking about a subset of C++, all of the character indexing for an array is going to be zeros based. And so this from version of index of, it searches for the offset within the array, which is the character string of the particular character, but it starts it from that particular parameter location called from. And we gave some examples about that. Then we also talked about the string tokenizer, which is an efficiency. It's a useful little library. A token is a compiler term representing a string separated by a delimiter, and a token is a string that has meaning in a particular programming language. And so for string tokenizer, we gave this example, and the nice thing about it is that you can specify the set of delimiters up front, and you keep calling string tokenizer, string tokenizer, string tokenizer, and it gives you the next character sequence or token as defined by the set of delimiters that you give it. And so how string tokenizer works, when you give it the delimiter array or delimiter character string, each position or each character is considered as a delimiter. And in this example, our delimiters are the colon and the semicolon. It starts out with the string you give it. It replaces each occurrence of those delimiter elements with a null character, and then it returns to you each string terminated by the null. And so string tokenizer is an alternative to make your life a little bit easier than using index of and substring. Any questions about this? No, no questions. Make sense? Yeah. All right. So let's take a look at the Raspberry Pi, and this is a high-level introduction. And again, my plans were kind of dashed because I wanted to I have my Pi here. I wanted to actually connect to it and get it going. You can connect it to the network, no problem. But the problem is when you want to access that device. I need to have another conversation with ITS. And so Raspberry Pi, not that Raspberry Pi. This Raspberry Pi is quite tasty, right? It also has a lot of utility. Raspberries are very good for you. So you can kind of have the best of both worlds. You can have something that tastes great, it's sweet and tangy, but it also, serving of raspberries is packed with all sorts of essential vitamins and fiber. 32% of recommended daily intake of fiber comes from a serving of raspberries. So you can eat your pie and have some very good health benefits as well as something that tastes great. Now, that Raspberry Pi is good, but this Raspberry Pi is also pretty sweet, right? It does a lot of wonderful things. It gives you a significant amount of computation in a small form factor. The Raspberry Pi is credit card size, and I have my Raspberry Pi here off on the side in a case, and it has a quad-core ARM-based architecture. A core is a processor, and this particular chip, which is the center of the Raspberry Pi, the credit card, the regular Pi version 4, 4B, it has 4 of these ARM-based chips on the same die, on the same chip. So it can do a lot of stuff, right? A lot of computation in a small package. And how this is achieved is with the so-called system on a chip, or SoC approach. And unlike the traditional, maybe you learned the von Neumann architecture, you have a high-speed communication substrate called your system bus, and then you hang all of your components that comprise your system off of this bus. And so you have the CPU, central processing unit, FPU, floating point unit, you have the IO device handler, circuitry or chipset, and attached to that IO are things like your mouse, your keyboard, all sorts of other devices like your network card. But unlike that, with system on a chip, they put all of this stuff on the same silicon instead of attaching them to a bus substrate. And what that allows you to do is put a lot more functionality and therefore a lot more power in a very small physical size. Because all of that bus circuitry, right, that bus-based approach, it takes real estate to do that. And so you have everything, your CPU, as well as your analog and digital I/O pins, just like on the Arduino, served up or enabled by this single chip. And here you can see the processor die. It has a cap on it to help with the heat dissipation, but also to protect it from RF radiation. Any questions about this? No? All right, you've all taken 140? Okay. And so why is the Raspberry Pi there? There's a lot of very interesting benefits that the creators of Raspberry Pi Enterprise to engender when they created it. But from our perspective for this course, what we're interested in is that it's portable. It gives you so-called low power edge computing, these devices that sit at the boundaries of the network, and you try in edge computing to keep your data close to your computation at the extremities of the network. When you put your or co-locate your data with your computation, you can have a lot more interesting types of high performance applications without having to traffic particularly large data sets back and forth across the network. And another goal of the Raspberry Pi organization was what I call CS, Computer Science for All. Now, CS for All is an important one, so much so that they also have affiliated with Raspberry Pi the device and the technical parts. There's a nonprofit called raspberrypi.org. You can read about it yourself. And their goal is to make computing a lot more accessible financially to all sorts of people worldwide. Now, this includes the development of educational materials, how-tos, tutorial, as well as the inexpensive deployment of the devices. In volume, I'm talking, tens of thousands or thousands of devices, you can get a self-contained computer, the Raspberry Pi being the heart of it, add a keyboard, a mouse, and some packaging and some cooling and a power source. And you can get these things down to about $50 to $100, depending on all the bells and whistles you want. And so the idea with the nonprofit is to engage people in creation of interesting devices, access to computation, because when you have the connectivity plus the computation, you have at your fingertips access to all sorts of information. And so raspberrypi.org is the nonprofit associated with that. And it's based in the United Kingdom. And they do a lot of very good work on a global scale. Okay, so that just says, not just being a technologist, but also enterprise to make a difference, however you view making a difference, right? And the Raspberry Pi organization has certainly done that and is continuing to do that. So the Raspberry Pi is not just the device itself, there's a whole ecosystem around it, just like we saw with the Arduino. We have the plain vanilla Raspberry Pi platform, which is credit card size, but we also see different form factors that are tuned for all sorts of environments. I'll direct your attention to the upper left-hand side of the screen, this orange and white module up here. That is a Raspberry Pi that's been ruggedized and packaged to stand in an industrial environment. And there are organizations now doing factory automation, brain's not working today, doing factory automation with the Raspberry Pi. And to do that, you need, of course, more I/O pins, but you also need it to physically survive potentially harsh environments, things that are humid, things that are hot, things where you might have a lot of vibration. And so this particular module on the upper left-hand side, your left of the screen, is an industrial grade Raspberry Pi module for factory automation. And then you have the plain vanilla Raspberry Pi, which should look very familiar. And that is sort of hobbyist and maker grade, which is useful for teaching as we're using it, as well as creation of all sorts of devices. Typically, they have a whole set of cases that will hold your Raspberry Pi. And these could be decorative because they look cool for various types of customization people enjoy. They also provide extra cooling. When you have this quad-core processor going full board, doing a lot of computation continuously, you have a lot of those circuits working, and you're going to get, as an artifact, heat generated. And so you really want as much as possible to keep your Raspberry Pi as cool as possible so that it will function well. If it overheats, it will shut down to try to save itself from damage. And so here in the center bottom row is an example of a case for the Raspberry Pi that provide the cooling fan. And if you can think of it, believe me, someone else has. There are all sorts of cases that do all sorts of things, including liquid-based cooling systems for high-performance type of applications. We also have Raspberry Pis embedded in various interesting form factors. This is a standard keyboard, and inside of it is a Raspberry Pi. And so with that, you just plug in a mouse, plug in network, and plug in a monitor, and you have a self-contained compute device. Now, granted, the Raspberry Pi only has so much computation ability, but for access to a server, cloud-based system, which is where we're going anyways, it's perfectly sufficient. And the nice thing is, let's say you have a grammar school or middle school, you can press these out in a factory very cheaply and almost give them away to the student body for use. The Raspberry Pi was designed to connect not just to an HDMI monitor, but it will connect to a standard television set through the right adapter. And so let's say you give this away to a kid in grammar school. He or she has access to a TV at home. You give this person an adapter and they can go up and running and don't have to look for a keyboard or any special display device. Any questions about this? No? All right. So we also, just like the Arduino, we have small form factor versions of the Raspberry Pi. This is the Pi Zero. Now, granted, it is not as functionally equivalent in terms of capabilities as the full-size Raspberry Pi or the credit card size, but is still a quite capable device for the size. Now, you would buy something like this if you maybe wanted to implement something like a kiosk where your computation is part of the device and it's a relatively small form factor. And so I'm only barely scratching the surface. This ecosystem is far beyond what I'm mentioning here, but there are all sorts of accessories you can buy, all sorts of different designs, and all sorts of sensors and actuators you can interface to the Pi to enable all sorts of applications. And it just so happens that most of the sensors and actuators that work with the Arduino also work with the Raspberry Pi, and that's on purpose. Okay. Any questions? No? All right. And so, oops. Uh-oh. So there are all sorts of interesting applications people have enterprised to create with the Raspberry Pi. And this is just a very small sampling of what people have done. Now, retro gaming, I'll direct your attention to the upper left-hand side of the screen. There's a big movement of folks who were gamers back in the 80s and 90s, the retro gaming movement, things like the Super Nintendo Entertainment System, Super NES, games like Donkey Kong, Galaga, Galaxy, and Pac-Man, Mrs. Pac-Man, all that stuff. There's a big movement of people who want or enterprise to implement retro gaming consoles as well as kiosks. Another one, this NAS box in the upper center frame, I direct your attention to that. NAS is network attached storage. The Raspberry Pi has the I/O connections, it has the networking, provides the general computation. So a lot of people implement disks that are network accessible and use the Raspberry Pi as a computation platform with which to drive that. People have implemented cluster computers. A cluster is nothing more than a high density amount of replicated computation for some purpose. And so we see here a number of Raspberry Pi units with SSDs, and they provide computation for some application, and they're networked together with some fast networking, specifically gigabit Ethernet in this particular case. Some of these applications are for entertainment, like the cluster computer, and others are just purely just because you can. Here, this is another interesting one. It's a Raspberry Pi Sugar Cube launcher. And so this particular person has a range sensor, just like what we have in our Key Studio kit. And when you put a coffee cup a certain distance away, this thing launches a sugar cube in the direction of the cup. And this person has worked out the right trajectory and speed for motors, some actuators, to spit this or launch this sugar cube into the cup. Another more useful type of application, well, sugar and coffee is very important, but another type of application here on the lower left is a wall-mounted Google Calendar. And so that's afforded by the fact that the Raspberry Pi is so small, you get a nice display, could be touchscreen, could be a regular non-touchscreen display, and you can mount this Pi on the back of the display, hang it on the wall, and implement your Google Calendar. So you almost have it maybe at your desk or on the wall somewhere for all of your appointments and managing your time. Now, this last one on the lower right, your right, is a pet feeder. Someone has gone through a lot of design. Let me see if I can get the sound going. I don't think I hear any sound. Oh, let's see. Let me, I lost the sound. Where'd it go? Where's sound? Sound, there we go. Output, exascalar. Okay. So let's full screen, slideshow. Go back to slideshow view. And why don't we continue? Yeah, I don't hear anything. This is just, oops, let me see. Nope. I'm sorry. Oh, there it is. And so this person has implemented a web accessible pet feeder with a manual override. They have an LCD screen, it's network connected. It uses an actuator and a little paddle that they just turn with a stepper motor, and they can feed their pets remotely whenever they want to. The water part they haven't done. Water is a little bit more tricky to deal with, but you can see it works quite well. Now, of course, if that's anything like my dog, the dog would try to tear the tube off the wall and try to release the animal feed when it's not supposed to. But all sorts of creativity enabled by this ecosystem. All right. So let's go forward and let's look at getting started with your Raspberry Pi. And so getting started, there's some basic ingredients you need. These are not the only ingredients, but these are things that you need minimally to get started. Now, I wasn't anticipating the HDMI and the keyboard and the mouse. I was assuming we could kind of unplug what we have in here when you're in BP310 and use the keyboard and monitors on your Raspberry Pis, at least when you're in this room. But minimally, you need the Raspberry Pi power supply. You need a micro SD card, and that micro SD card acts as the hard drive for your Raspberry Pi. You need a USB keyboard. 2.0 will work fine, doesn't have to be modern. You need, of course, the Raspberry Pi itself. Whether or not you have a case is really up to you. You can choose to get a case or choose not to get a case. For the uses that we have, we're not going to drive it terribly hard to generate a lot of heat, but it doesn't like to be in very, very hot environments, right? So you don't want to have it in an 80, 90 degree environment with, 60%, 70% relative humidity. And then you're going to need a USB mouse, and you're going to need some kind of display device, HDMI in particular, that you can plug directly into the Raspberry Pi. It drives up to 2 HDMI monitors. And so the Cana kit is in each one of your kits. I've supplied that just in case there were those who did not get the device. And the Cana kit provides all of these except for the USB mouse and the USB keyboard. I've also included in each of the kits one of these 7-inch LCD displays. Let me see if I can, there we go. One of these 7-inch LCD displays. It's touchscreen capable. And this is just so that you would have a display that you could use with the device, the Cana kit supplied in each kit, if you need to. This is going to require some assembly. It's a little bit wonky on the assembly. And what my plan is on Friday to use about half of the first session to do the assembly for this thing and to get your Pis started, and then use the afternoon session for the Project 6 device-to-device communication. Okay, I made probably like 10 different mistakes and ended up having to unscrew and rescrew in and unassemble and reassemble. So I'd like to help you out with that so you don't make the same mistakes that I did. The screws are a little bit tight, but the device works well once you get it up and running. Okay, and so The Raspberry Pi, as I said, will also accept any HDMI display, which I believe these displays in this room all are. Okay. Any questions? No questions? Make sense? All right. And so capabilities. The Pi is a very capable little device. It provides gigabit wired Ethernet, so you can actually plug in a network cable. I'm not sure how the Clark IT architecture is, but if it's anything like my previous institution, you can't just go unplugging jacks and plugging in your device. You'll set off alarms, and I'd assume they're probably the same here. But nonetheless, you can plug in a so-called category 6 or Cat6 wired Ethernet cable into the Pi, and it will engage in DHCP, Dynamic Host Configuration Protocol, and attach itself to the network if your network has enabled the ability to have devices join dynamically. It also provides 802.11 Wi-Fi wireless communication. And so you can connect it to the wireless access point. In fact, I have my Pi connected to Clark Guest Wi-Fi as we speak. I tried to get Zoom running on it, and I actually planned to do this particular module from my Raspberry Pi, but I wasn't able to get Zoom to work on it. There's some driver issues and some display library issues. But that being said, this capable little device can do Bluetooth 5.0, which is backwards compatible, and also Bluetooth Low Energy. So it is very useful as an IoT device, but unlike the Arduino, this is what's called a system on a chip single board computer. It's an actual general purpose computer, and it's a lot more capable. People do gaming on the Raspberry Pi. People do cryptocurrency mining on the Raspberry Pi. People do all sorts of stuff on the Raspberry Pi. It's a capable little device. It has 26 general programmable I/O pins. And so, like we saw on the Arduino, you can specify a digital input, digital output, analog input and output. So the Raspberry Pi, this credit card size version, can drive quite a few I/O devices. It also has 7 ground pins, a lot more than we saw the Arduino had, which only had, I believe it was 2 ground pins. So it was intended to interface with the outside world much more substantially than the Arduino. But again, the Arduino is a microcontroller. And what you find the big difference is between a microcontroller and single board computer or system on a chip is that the system on a chip was always intended, like the Raspberry Pi, to be a general purpose computer. And so Linux runs on it, and you can program in Python and C++, Java, CircuitPython, all sorts of stuff. It is just another Linux node, Linux computer. A microcontroller was purpose with adding single purpose computation to some device. And so what we saw when we looked at the LCD display, we can use it to drive a display, we can use it to read sensors, we can make it network accessible. And so typically microcontroller is tuned to just a single application, whereas the Raspberry Pi, as a general purpose computer, you can run arbitrary computation on it. So you could use it for maybe driving a kiosk, or you could use it as your desktop computer that you use to connect into Clark's network or do homework and things like that. You can run word processors on it, anything you can do on Linux within the limits of the quad core processor and the amount of RAM and hard drive you have, your SD card. Within those resource limits, you can do anything on the Pi that you could with a laptop or any other general purpose computer. Okay, any questions about this? That makes sense? Yeah, all right. And so what does the Raspberry Pi run? Well, it runs Linux. I'm sure somewhere somebody's trying to get it to run some other operating system. I don't know how successful they are. But the most popular Linux that it runs is something called Raspbian, right? Raspbian is nothing more than this Debian Linux distribution. And I'll explain a little bit what distributions are. And as a Debian variant, it supports all of the Debian commands like apt get, and all those things for managing applications and installing applications over the network. Now, the Raspbian variant that they recommend you use is the 32-bit version, but it is a 64-bit architecture, and you can install 64-bit versions of Linux on it. Some people use a Raspberry Pi as a firewall or security device. You can install something called Kali Linux, which is highly tuned to implementing fixed network security appliances. And you can do all sorts of stuff on the Pi. There's an absolutely huge community out there with lots of documentation, not necessarily in textbooks. Any questions? No questions? No? All right. And so for the IO in the IoT kits, you'll see, I think I kind of jumped ahead, 7-inch LCD screen. It's touch sensitive. You'll need to build this monitor. Again, as I said before, we'll spend probably half of the morning session on Friday doing that. There are many opportunities to make mistakes on this thing, like I did. You're gonna have to find USB keyboard and mouse. I'm assuming you can just unplug the ones in here and plug it into the Pi, but please, if you do so, make sure you plug them back in to the units here. At the URL down the bottom is a great getting started guide to walk you through just plugging stuff into the hardware. When you first boot the Cana kit, it'll ask you to install the operating system. But if you bought your own Pi and your own SD card and it's not prepackaged, you're gonna have to install something called Noobs. And Noobs is a piece of software that comes up in a menu and makes it easy for you to image or to install an operating system on your SD card. And so there is a URL that I will give on Friday where you can download and put Noobs on your SD card. And then when you boot your Raspberry Pi, Noobs takes over. And with a network connection, it can do everything over the network in a nice, clean way. Okay, any questions about this? No? All right. And so let's look at the command line. As I said, Raspbian is a Debian Linux distribution. And what makes Linux Linux is the so-called Linux kernel. The kernel is the heart or is the operating system. And more formally, an operating system is purposed with abstracting limited resources, namely the hardware and all the other subsystems that comprise your computer architecture. And so the kernel sits between your applications and your CPU, your I/O subsystem, your memory, that's your RAM, as well as your disk and your network. And it presents APIs that manage and share all of these limited resources among the many applications that might enterprise to use them. And so the Linux kernel is a so-called monolithic kernel. It's a big ball of software, and there are debates in the operating system community as to what is the quote-unquote right approach for how you implement the kernel, the share of hardware resources through APIs to applications. Now, Linux was created by Linus Torvalds, who took operating systems at Vrije University in the Netherlands. And there's a famous argument that goes back and forth between Andrew Tannenbaum, who taught the course, and Linus Torvalds as to what architecture is best for an operating system kernel, whether it's something called a microkernel or something called a monolithic. Now, you know, in any sort of argument, debate, discussion that goes on, in a sense, they're both right and they're both wrong. These approaches have their utility depending on what you're enterprising to do. But nonetheless, Torvalds, Linus Torvalds, named it Linux after himself, and this monolithic kernel, it kind of scrubs away abstraction. And when you scrub away abstraction, you don't have all these different layers of APIs that call APIs, and you can make things really, really small for that reason. And that's why you see Linux driving a lot of embedded devices from enterprise applications down to little button-sized compute platforms that are hanging off of devices to make them network accessible. And so this Linux kernel does the basic management of your system, but the Linux kernel is not very friendly for us to use, right? You need a bunch of other utilities on top of that so that you're not dealing with tracks and sectors to access bytes on the disk so that you're not dealing with blocks and IO channels when you're dealing with transferring programs from disk to memory, for example. And so all of these libraries, system libraries that you have, they take the raw services of the kernel and then make them much more easily usable to application developers. Now, the applications sit on top, and these applications can range among a host of things, including making it look nice in the form of a graphical interface, as well as certain productivity tools like IDEs, word processors, video conferencing programs, and things like that. And so driving these devices are so-called device drivers, and these device drivers translate between all of the intricate details to control the circuits of these devices and the channel of data that you can send data to or get data from. So if you collect together all of the productivity tools, all of the drivers, all of the interfaces and programs, that collection of drivers, interfaces, tools, and programs is called a distribution. And so the Debian Linux distribution is a particular choice of all of those things that someone thought was useful and what it means to be a good operating system. Now, there are umpteen many Linux distributions out there, and they carry various assumptions. On one extreme, you have something like Kali Linux. Now, when you set up Kali Linux, and more correctly, I shouldn't say Kali, Gentoo. Gentoo Linux assumes that you know a lot about the underlying hardware in the system. And when you install Gentoo Linux, it asks you a lot of different questions about a lot of different things. And it only installs minimally those things that you tell it that you intend to use. And so Gentoo is on one extreme where you're directly selecting those pieces of an operating system that you need for an application. And typically with Gentoo, you're building an appliance, a singularly purposed device where you don't want all this other stuff, nothing more than absolutely what you're going to use in your application. And then at the other extreme, you have things like Ubuntu Linux. And Ubuntu Linux was intended to compete against things like Mac OS and Windows franchise, in that you have a nice, friendlier graphical user interface with lots of tools that make the experience very graphical and much more usable. And so in the middle, between those two extremes, you have all sorts of choices that people have made. And it's really not that big of a deal to create your own distribution, right? You just package a Linux kernel, and typically with a distribution, you start with an existing distribution, and you might add and subtract some tools, package it up, and make it available for people to use. And people create distributions in the corporate world all the time. Let's say, for example, you were Price Waters, or name some accounting firm or some financial firm. You can package up a Linux distribution with certain tools. Maybe they're tools for the trading desk that you use in a particular group. You package it all up. Someone starts anew. You flash this kernel, this distribution onto that system. They boot, and they have everything they need to do their job. And so people use distributions for all sorts of reasons, including the deployment of devices within or desktops within an organization. Any questions about this? No questions? No? All right. Okay, so one of the big ways or main ways or major ways, popular ways that you interact with a Linux distribution is through the so-called command line interface, or CLI. And so the command line interface, it draws its lineage from a teletype. And I remember, well, reading about teletypes. I've never actually seen one, but there's a growing community of people who are trying to resurrect old teletype machines. And so before monitors and cathode ray tubes, in the beginning or earlier days in computing, you had a printer actually printing out your interaction with the computer, and it was all text-based. And so you'd sit at a so-called teletype machine, and I have an example of a teletype of video, short video, in the frame on your right, and you type just something in. It would echo or type out what you're typing at the keyboard. You'd hit enter, that command would go to the computer, and then the computer would do something, and whatever output someone printed or that program printed, the teletype would type on the screen. So I'm gonna play this video to give you some experience with a teletype. You can kind of hear it buzzing. And you can imagine you went through a lot of paper just by interacting with your machine on a teletype. And that was what early displays were for computers. And what we see as a command line interface is nothing more than a modern version of the teletype. It's actually something very pleasing about listening to it and watching it. I don't know why, but okay. Yes, that's a good question. If you made it, that's a great question. Delete might have been after the teletype because you couldn't really go backwards. You wouldn't like, back in the days of typewriter, you'd have like this thing called erase tape. But I'm not sure teletypes had them. They just kept going. So you probably just hit enter. Delete was something that came when you had cathode ray tubes because you were able to have a cursor and make it move. That's a good question. I can find out. I can ask a friend of mine and find out. Yes, question. No, no. This is a video I found of a teletype. It's it actually it's an automated typewriter, literally, right? And that was what they had at the time. Now you're talking teletypes they had in the 30s through the 50s, right? And so if you go back to 30s and 50s, TV was really young, right? And so TVs were very basic. They used UHF, radio frequency, not cable, no digital signals. And TV could not display the outputs of computers back in the 30s to the 50s. And so they used what they had, typewriters, and they used that as the method for displaying the text because that's how people trafficked in text predominantly at the time is using typewriters. And so to answer your question, it's not my typewriter. It is basically derived from a typewriter that they have used to display ASCII characters. Any other questions? No? And if we go back to our discussion about carriage return and line feed, that is an artifact of the teletype, right? Carriage return meant to take this writing element and bring it all the way to the left. You're returning the carriage to the left, getting ready to start typing another line of text. And line feed was to advance the drum so that you could write on another fresh line of paper. But in a typical session, I'd imagine you'd use a lot of paper if you were dealing with a program that did some printouts and a lot of other interactions. Any other questions? No? All right. So on the left-hand side, this is a command line interface, and it's really just a digital version on an LCD screen of a teletype. And if you think about it, we're really a lot more primitive than we like to think we are, because here we are using a digital teletype now, over 80 years removed from the teletype. And so with this command line interface, like the teletype, you're typing in commands and the computer is taking these commands. And if that command or thing you type in, once you hit enter, it will interpret what that command means. And so that command is either something that matches the name of a program in your system that does something, interacts with the kernel, or it won't understand what you're doing. So let me switch in this particular figure on the left. That's the command line interface on the Raspberry Pi. But I'm going to switch to the command line interface on Mac OS to show you some of these commands. All right, so with these commands, and I'll just talk about this and then switch to the command line interface, you have a bunch of different tools that you can use to manipulate the file system, that is to navigate the file system, to open files, to close files, to examine files, to delete files, rename files. You can navigate around your directory. So you can go into a directory, out of a directory, just like you can with folders through the user interface in something like Mac OS and Windows. There are certain command-based things like examine what's called the history buffer, and I'll talk about that by example when I get to the command line. You can examine where you are in the file system to kind of interrogate it, to say, where am I? What location am I at currently in the file system? You can use it to examine your identity. What is the username that you currently have assumed? Bits about the network, etc., and about the operating system. So why don't I go into the command line interface in Mac OS, and I have a window up. Let me share that screen so it shows up on the video. And so I'm on Mac OS in the command line interface, and Mac OS is based on BSD, Berkeley Systems Division Unix, which is a so-called microkernel. The difference between a microkernel, which is what BSD is, and a monolithic kernel, which is what Linux is the philosophy about what those services, like your file system, where they should reside. In a microkernel, it says the kernel should be relatively very small and provide almost nothing outside of the ability to launch processes, to start programs in their executable form, and basic memory management and basic shuffling of data to and fro different places in the operating system. Things like a file system and the network in a microkernel are implemented as so-called low-level services. And the philosophy with a microkernel is that when you have these abstractions of operating system facilities as these services, it makes it easier to replace them and to swap them in and out and extend your system. Now that has utility, and I have to admit, in full disclosure, I'm more of a fan of microkernels than I am of monoliths, but at the end of the day, a pragmatist in me says, use what's right for the job. A monolithic kernel puts that all in one big ball of software without as much abstraction. But with that, you can extract a lot more efficiencies because each one of those service calls it slows down your ultimate performance. And so here I'm in Mac OS at the command line interface, and you'll notice we have a prompt here, and it's asking me for input, and it's running a shell, which is an interpreter program. It sits there in the background, and every time I hit enter, it's going to take that command and look or try to make sense of what it means. Now, you'll notice at first, when I've logged in, I'm put in something called my home directory. Now, this particular naming scheme, CS008033, that was assigned through ITS when I logged into the machine, and also when they set up my machine, they managed it. And it put me initially in my file system in my home directory. Now, the home directory is where you start out when you log in to the system. And one of the things you notice I did, PWD, stands for present working directory. It's one of those interrogation commands. When I type PWD enter, the command line interpreter takes that PWD text, it looks it up and says, does this match a program somewhere? Yes, it does. I'm going to go ahead and load and run that program. And so PWD, or present working directory, shows you where you are in the file system. Now, unlike Windows, in Unixes, and this is standard whether or not you're a microkernel or you're a monolith, the path separator, how you delimit folders, if you will, in your hierarchical path, your directory structure, the path separator is a /, whereas in Windows, it's a \. And so it says, okay, starting out, going from left to right, we have /, which is the root of my file system. And then I have a users directory, and then gwholeness, which is my home directory. Now, in my home directory, you can put whatever I want, and I have permissions to read, write, or execute as the owner of this account, gwholeness. That home directory, I have full permission to do anything I want for all the files that start, or subdirectories that start from that home directory. And so associated with every credential, every username that can log in is a so-called home directory, right? So if I were to ls is another command, stands for listing, it shows me all of the objects that are on my file system within my home directory /users/gholness. Now, some of these objects, the two major flavor of objects you can have on your file system are files and directories. Now, a directory is nothing more than a special type of file. And if you were to open up that special type of file called a directory, it would contain a list of things that are on your file system. And so you can think of a directory as kind of like the table of contents in a book. It's a bunch of data, and that data has numbers telling you where certain things are located in the book. And so the two different type of objects you have in your file system are directories and files. And you'll see here, I have test.html from last time. I forgot what I was doing. I think I was demonstrating valid HTML to myself. So clears the screen. And I'm going to do an ls again. And I'm going to clear the screen and do a different version of ls. If I say ls space -l, -l is a so-called command line switch. Now, whenever you specify a command on the command line in any sort of Unix, most of these commands, the style when you want to change the way these commands work is with a so-called command line switch. Now, these command line switches are usually of the form where you give a dash and then some character, and that has meaning. And I'll show you a way to find what these options are. But before we do that, let me try ls-l. Gives me a so-called long listing of where I am in my directory. Now you'll notice here, some of these things are directories and some are files. Here, along the first column, I have this weird coding scheme. And this weird coding scheme, the first character, for some entries, it says D here. For some entries, it has a dash. Now, D means that this particular thing is a directory. And you can see here, desktop, it's a directory. Applications, it's a directory where all my applications are. Test.html, if we go to its descriptor, it has a dash, that means it's a file. Now, with these directories, like folders in a graphical interface, you can navigate into a directory or you navigate out of a directory. Now, to navigate into a directory, you use cd or change directory, and cd expects a parameter, which is the name of the directory. So if we say cd, let's say applications, you notice something else happens. I said cd space applications, and I hit enter, and you notice my prompt has changed. It's changed from gholness tilde, and tilde means home directory, to applications gholness. So it's telling me I'm no longer in home gholness. I'm now in a directory called applications, which is underneath home gholness or folder. So let me clear the screen. And now let me do a pwd, present working directory, pwd. And you'll notice if I ask it, where am I in the file system? I'm now in users gholness applications. Now, if I did a listing of what's in applications, ls, I should have other stuff, ls-l. Oh yeah, it's the other application, my mistake, yeah. So you'll notice what I have in applications directory is different, I don't have anything, from what I have in home gholness. Now, one of the things I could do when I say ls, I notice here, I'm currently in the application subdirectory. If I want to go back up, I say change directory, ... goes up one level in the directory hierarchy. So if I hit enter there, and I do another present working directory, I notice I'm back in users gholness. And if I do a listing there, you can see I have all that stuff that was there before. Any questions? No? Now, oftentimes, productivity-wise, when you're working on something, you might go to a different directory, do something, return back to where you came from. They've implemented in most Unixes, in most command line interpreters, something called the directory stack. Now, the directory stack works just like the stack data structure. You type push D to push a directory, and then the name of the directory you want to change to. So pushd is like saying change to this directory, but do it in a nuanced way. I want to remember, and it uses a stack to do that. I want to remember the directory that it came from. So if I say pushd applications, now it shows me what the status of that stack is and changes me or navigates to that directory. The stack is read from left to right. At the top of stack is applications, and that's the current directory I'm in. The next thing on the stack is my home directory. So what if I said pushd, let me verify I'm in applications, pushd user lib. Now I'm in user lib, right? Now, if I say popd, I'm popping the stack. It brings me back to applications. Popd, pop directory, brings me back to my home directory. And so that makes it a little bit easier if you're switching to one directory temporarily to do something and you want to come back to where you are. The directory stack is immensely useful. Okay, any questions about this? No? All right. And so do a time check. Another useful thing is the history buffer. If I type the word history, it shows me a numbered list of all the commands that I've written. And so often when you're using a system, you might repeat some commands. And it's kind of nice to be able to go back and replay those commands without having to type everything all over. So let's take a look at command number 516. That's the 516th command that I've engaged in with a command line interpreter. And so what I can do is if I say exclamation, which is called bang, 516, the number, hit enter, it'll replay that command. So it's a nice, useful thing. Now, I could also, history, I could also, with that command replay, or bang, as it's called, I can also search my command history. So let's say I did a history, right? No, I did a clear. So if I said exclamation CL, it'll search back through the command list for something that matches CL, and the first occurrence of that, it's going to repeat that command. So if I hit exclamation or bang CL, it finds clear, and then it repeats that command. Any questions about this? No? All right. So what else? We talked about file system. We talked about history buffer, bang, which, okay. Now, a lot of times you want to find the location of something, like which PWD. And what the which command does, it searches through all of the directories it can find in your system, and it looks for the occurrence of that particular program, which is what the commands are, they're just programs, and it gives you the full path name to where you'll find it. So if I said which Python, it's in /user/bin/Python. Okay. Any questions about this? No? Now, of course, these command line commands are sometimes very hard to remember, right? What options do I have? How do I use it? There's something called the manual pages in most Unixes. And this is a standard thing for most command line interfaces. And how you use the manual page, you type man for manual, and then the name of the command, like ls, give me a listing. And when you do that, it gives you a little sheet, if you will, that tells you how to use the command. And so here, if I said man ls, it says ls, gives you a listing of the directory contents. It tells you how it behaves, and then it gives you a bunch of options, I'm hitting enter here, that it uses. So if I say ls, and it's alphabetized, -l, I can find out exactly how it works. -l, list in long format, a total sum for all the file sizes output. And so it gives me a complete accounting of all the different options I can do for each command. So for example, and I type Q for quit, clear, man, PWD, manual page. PWD, return the working directory name. And you can display the logical directory or the physical working directory, all sorts of options. Okay, so lastly, talking about identity. Who am I? You name if config. So who am I? Man, who am I? I know what it does, but it's just like, who am I? It tells you what is the user account that you're currently logged in as. And I'm logged in as account Holness. Now, of course, if you had the password, you could assume the account identity for just about any account for which you had the credentials in your possession. So it can be useful to interrogate the system and ask what your identity is. Another one, if config -a, talks about the network bits for the configuration of your system. Now, if I type that, a whole bunch of stuff comes swirling by. And in this particular case, it lists all of the interfaces that I have on my machine. And it has the IP address for those interfaces that are currently connected to a network. And so you'll see here, let's see, I think I'm EN1, EN2. Let's see which one I'm connected as. You have a lot of interfaces on a standard. Here we go, EN0. EN0 is my live interface. That's my wireless. I'm connected to Clark Wi-Fi, or should be. Sometimes it takes me onto EduRoam. And you'll notice here, INET, that specification, that's IP version 4. INET 6 is IP version 6. So that's your IP version 6 IP address, but the one of interest, IP version 4, my IP address is 140.232.232.94. And this is my network mask. So that's 4, 8, 12, 16, 20, and C is 1, 0, 1, 0, no, ABC, 10, 11, 12. 1, yeah, 1, 0, 1, 0. So I have about 25 bits or so of network mask. I'd have to verify that. But I have my network mask, and I have my IP address. Okay. Any questions? So you can interrogate your system to find out things like your identity, how you're connected, and so forth. So if config, who am I, you name. All right, so why don't we pop back to the slides? Any questions about that? No? Okay. And so how much time do we have? We have about 4 more minutes. Okay. And so let me go through this part. Let's talk about remoting. And so the most Unixes are so-called network operating systems. They live very nicely on a network, and they were intended to be connected to one another. And so one of the powerful features of most Unixes, BSD, Linux, all sorts of Unixes, is this ability to do things remotely. One of the big breakthroughs in networking is so-called X Windows. X Windows was created by Bob Scheifler and Jim Geddes. I had the good fortune to work with Bob Scheifler when I worked at Sun Microsystems. And X Windows was one of those examples where they accidentally discovered something that they weren't originally intending to. And so they were enterprising to do remote or distributed debugging of systems that were network connected as part of what was called Project Athena at MIT. And so when you're doing distributed debugging, well, you're on your machine here on the right, but you want to know what's happening on another machine that's connected to you by a network. So how exactly do you do this? Well, everything that occurs graphically on that other machine, you want to somehow send that some representation of what's happening graphically back to where you are so that you can display it. And so you take everything that's on that remote target, things like the windows of the graphical interface, the buttons, the text, the check boxes and all that good stuff, and you want to send information across to where you are and display it where you are. And so what happens is you treat what you're doing on your machine as a special type of client. Let's say you click a button, you type in a field, that client sends a request to a server called an X server on that remote machine. That server does some work locally. It does that graphics work. And then whatever the result is, now the button is painted as being pressed in, it sends back a response so that you know what you should draw on your local machine. And so that particular system, X Windows, which grew out of debugging, turned into a remote display technology. Okay, and so the client receives the result of what that graphical interaction is and then draws it locally. So with this X Windows, once it's installed on the endpoints, the X client is on your machine and the X server is on the other machine, when in truth, X clients and X servers exist on all the hosts so that you can do arbitrary display and request of display across different machines. And the beauty of this, as long as the X protocol is implemented, it doesn't matter which distribution or which version of Linux you're using, you can display what's on that machine on your local machine and use it graphically as if you were sitting at that remote desktop. Any questions about this? No questions? All right. And so I was hoping to log into my Raspberry Pi and display the Raspberry Pi display on my Mac laptop, but there's some issues in trying to remote into other nodes when you have a node on guest Wi-Fi and one on Clark Wi-Fi. And then I tried putting my laptop on guest Wi-Fi, and it seems like those ports are being blocked. So I have to get that resolved. So with that, we are now, that's time. That's 1/4 past. So we'll end there and we'll pick back up on Friday. So please look out for the new assignment. I'll post it tonight. If you have any questions further about Project 5, please don't hesitate to ask. Okay. So I'll see you all on Friday. Oh, this week. Yes. I want to remind you that the computer in this